These are some notes on JMESPath. A query language for JSON, which is JavaScript object notation. This is another app for your Necktop, which can be helpful to have, because sometimes you get back JSON from a CLI query, a command where you're asking for information, not necessarily doing something, and you only want a particular part of it, so you need to just have this JMESPath language on your Necktop. We don't know what JMES stands for. I like to think it stands for JSON, made easily searchable. Could do, but it's probably something to do with the fact that the website is written by James Sayawini, who created it, and his talk is still on YouTube called Becoming a Command Line Expert with the AWS CLI. Evaluate. So if we've got first name, colon, John, it means give me back the value associated with the key. That's what evaluate means in this presentation. A few other things to be on guard about. First position is second position for computer scientists. They count the first item in a list as 0, so we have 0, 1, 2. Now intuitively you'd say, if there's a range like 0-3, 0 to 3, that covers 3 items. It's absurd that it could cover 4 items because 4 is bigger than the upper bound. All numbers beyond the upper bound are off limits. But if we assume the lower bound is inclusive, 0, that's in the game, and the upper bound is also inclusive, well, it covers 4 items. Watch 0, 1, 2, and there's the 4th item labelled with a 3. So what was wrong with the thinking that said it was absurd? Well, it assumes that the way number words are used was to count. It assumes that the number word, or the word used when it's being used as a number word, is an existence claim. But of course we know that's not true. If someone talks of the first floor with a building, it doesn't mean that one floor exists, because they've mentioned one or first. So ranges, be on guard with them. They're using the counting words that computer scientists use. That hyphen should trigger a thought in you that makes you think, is it the stick being used to count things? If so, there could be 4 objects in a range that says 0-3. And with the few tools in the box that we can use with JMESPath, I'm going to keep mentioning the stick. We're going to meet the unwanted upper soon. We've got the index is internal. What is that about? As if someone took the last pages of a book and chewed them up so that the index was inside them, rather than external. And the segregating star, and we'll meet those in turn. So the most basic idea of JMESPath is an identifier. So the box here is the JSON we're querying, and here's the query. You name a key, we give you the value for the key. So if you put A in the box like that, you get back foo, because it's A, foo. Next idea, a sub expression. A.B.C.D. Sub means like under or within, really, within. So what's going on here if you see A.B.C.D? Well, in JSON we have something called nesting. Instead of just a key and then the value, we have a value with lots going on in it. So you could have fruit apple, but also enclose the value in those squiggly, curly braces, knobbly curling braces for nesting. Here is some JSON, and we've gone 4 levels deep. Orange fruits, 2 levels deep. Third set of brackets, 3 levels deep. Now if I wanted to get to something within those square brackets, this is where the sub expression comes into play. I could do fruit dot orange fruits, and that's going to give me the value of orange fruits. Of course, orange fruits is itself sort of the value, because it's part of the value of fruit, but that's what we do, we use the dot. So JMESPath allows us to use sub-expressions to request nested values, dot notation. Character on the right hand side of the dot is a nested key. A.B.C.D goes within A to get B, C, D, and then it says, well, what is it D? Gives us back value. So now we're going to kind of step back and look at some of more fundamental issues. What is an object in JSON? Here, this is the ops object. So yes, it is a key value pair, as we introduced that concept already. It's a key value pair, but by naming the key, that's the name of the object. So that's what we do. The value, just like before we said, has been encapsulated in those knobbly curly braces. Could we just replace them with square brackets? We'd have an array then. Maybe that's a good thing, because square brackets indicate an array. And then if you look, there's a comma here and a comma here, and those are elements within the array. Would that make a difference? Probably not. We'd have 3 items in the array, like that. So maybe we could just replace those curly brackets with square brackets. Why do they choose to use square brackets sometimes? Here we've got a list, a comma-separated items making up a list. So what does this mean? What does it tell us when the square brackets are being used? We'll consider this question. What is a person? They're kind of a hodgepodge of properties. They've got a height, a particular skin colour, a particular age, a particular first name, usually a particular nationality, personality. Now, if someone asked what comes first, your height or your weight, it doesn't really make sense. You've somewhat misunderstood what's going on here. Neither. And that's why I say people are more of a hodgepodge or bundle of properties. The order doesn't matter. Now, someone might come back and say, well, sure, but we could assign an order. We could put the 0if height as 0if property being height, the first property being skin colour, the second property being first name. That's like standardization, making things orderly, which don't have to be, but there's a bit of a benefit to it. But in response, with JSON and I think code in general, that would be actually misleading. Ordering these properties would imply that they're the same kinds of things, and they're not. A nationality is not the same sort of thing as an age. There's something about this at the top, mango, kiwi, banana, apple, which is good or appropriate, because kiwis and bananas are the same kind of thing, and putting age, nationality and first name in square brackets is inappropriate. Can we say why? Aren't they the same kind of thing? They're all properties of a person, just like they're all fruits. But that's the point. Because they're properties, an array is inappropriate. We don't use arrays to list properties. The thing at the top here, the fruits, these constituents co-occur. These constituents form a complex, united by a logical form. Oh, that is really a way of putting it. But the point is, JSON relies on a distinction between things and properties. There may be cases where it's not clear whether something is a thing or a property, and we're going to look at a tag, which is an interesting example because it's both a property of an instance and a thing in itself with properties. But these cases aren't a problem, that's fine. Something can be both. Relating this to the previous presentations, Gilbert Ryle, the philosopher, talks about things called category mistakes. Imagine there's someone walking around a university and they say, there's the chemistry building, there's the gym, in this building we have a cafe. And you go around all the buildings, and then they turn to the tour guide and say, well, where's the university? Arises out of all those buildings, they've made a category mistake. Don't worry if you don't understand this, it's going into philosophy a bit, but if Descartes could use JSON, he'd probably want to say that we have two bearers of properties, a body and a mind, and the body has various features, the mind has various features, and most people would probably say that's not correct anymore. So we speak about how we think the world is constituted using our code sometimes. EC2 instances, they're like fruits. So we're going to list them in these square brackets. A tag, just like a type and a state, is a property of an instance. And let's zoom in on that. You can see here it says tags, colon. We've got an opening square bracket. It finally gets closed down here. Tags are, as well as being properties of instances, things. They consist of a key and a value. So a tag is a bunch of property because it's a thing. But the key and the value That's akin to the age and the nationality of a human being, or age and name. And that's why we don't list the key and the values. We have them as comma-separated items within curly brackets. You can see there in green the curly brackets containing the key and value for one tag. Of course, here's another key and value, meaning here's another tag, because the tag arises out of the key and value. You can't say where is the tag, that's a category mistake. So just clearing up some terminology going forward, what is the object? Is it the thing in green or the thing in blue with JSON? I think the answer is kind of both, actually. People will often say that an object is a key value pair, which would mean that green is an object, but blue is also an object because it is contained in curly brackets. So that's my reason. I'm saying that if it's contained in curly brackets, it is an object. A sequence or a list, no. Key value pairs listed one after another, where list doesn't mean it's a list with capital L in square brackets. We're going to have a name that's known as an associative array. And we're going to look at some other words for that in a minute, as well as being an object. This website, which is w3schools.com, say JSON object literals. Those are surrounded by curly braces. Okay, so JSON object literals. They contain key value pairs, plural. Keys and values are separated by a colon. Keys must be strings and values must be a valid JSON data type. String, a number after that colon, another object after that colon, an array after that colon, a boolean after that colon, or null after that colon. And each key value pair is separated by a column, comma. They say it's a mistake to call a JSON object literal a JSON object. JSON cannot be an object. JSON is a string format. Now, this generic term, associative array, is expressed in different ways in different languages. For example, in Python, released in 1991, named after Monty Python by Van Rossum, they call it a dictionary. And you can see here, type, their built-in type, dict, associative array, or dictionary of key value pairs. Python makes a distinction between lists and tuples. Lists are written as 1, 2, 3 in those square brackets, and tuples are within rounded brackets. And they can be used as keys of dictionaries. That's a bit of detail, that doesn't matter, we're not going to talk about tuples. Ruby came a few years, 4 years after Python, and Yukihiro Matsumoto was aware of Python. I think he said he didn't find it to be truly object-oriented, because it's not necessarily object-oriented, Python. It can do other things like functional programming. And they use the word hash for that, for this thing that contains key value pairs separated by commas. Hashes enumerate their values in the order that the corresponding keys were inserted. Grades equals Jane Doe 10, Jim Doe 6. So we've got that comma separation here. Clearly a slightly different way of expressing things here. And they say here you could write it like this, and this is slightly more similar to JSON. We've got the curly brackets on the outside. There's no angle bracket here between the key and the value. And then if we go to JavaScript, which is clearly related to JSON, we're told here all objects behave as associative arrays. This forum answer just tells us, I think of arrays as saying such and such is this. So we're saying a mango is a fruit, a banana is a fruit, whereas with objects, we're saying this thing has this property. So it's is and has. And they go through examples we've seen. Arrays have an order for the elements in them. There's no order to the things to the elements in an object. So we've looked at identifiers, we looked at sub-expressions with that dot notation, we then looked at how JSON works and the importance of square brackets and curly braces. Now we're going to move on to a new idea in JMESPath, index expressions. And we can already see that if there's order within the elements that are in square brackets in an array or a list, index expressions are going to be useful for those things and not so much for objects. The JSON website says an array is an ordered collection of values. Begins with a square bracket, ends with a closing square bracket, separated by a column. We use a comma for the elements in it, and they use these strange diagrams which you can cycle around. So you might have a value. If you have to cycle around to get another value because you want more than one value in it, you've got to get a comma along the way. Not everyone's a fan of those diagrams. So everything is arranged in an array, and we count from 0th. Just remember that. Sometimes the word list is used. Make sure that's doing work in your head to make you think of an array when you just see list. Someone might casually say we list the properties of an object, but they don't mean list. Array, capital L for list. So if you just put in 1 in square brackets, you get back the first, not the 0th item in this array, B. If you specify an index that's larger than the list, a value of null is returned. You can also use negative indexing to index from the end of the list. So does that mean the first item is counted as -0? That seems pretty reasonable. -1 refers to the last element in the list. -2 to the penultimate element. Try it out in the example above. You can combine identifiers, sub-expressions, and index expressions to access JSON elements. Here we have a list. If we put in -1, are we going to get E? No, F. That's the first one from the back. So far we haven't got anything in our toolbox for getting one particular key from an associative array for a bunch of properties of an object. You might think, well, that's what a sub-expression is. No, that's for a property of a property of a property. That's what that nesting idea was about. And that's not the same thing as one property among many properties making up or possessed by a thing. So we're going to get a tool for that. Yeah, index expressions locating items in an array by their position, via their position. Let's look at an example combining the things we've just learned about. So let's break down this example. If this looks confusing to you and you're new to JSON, we've got some nesting going on because we've got an opening curly bracket, a third opening curly bracket, a fourth opening curly bracket, and we haven't closed any yet. So 4 levels deep, the value of C is an array, we can see that. There are 2 elements in the array because I'm looking for that overarching comma, which is there, which is outside of any curly brackets. So let's mark it up. There's the outside object. The value of A is an object. I've put that in blue for the value of A. The value of B, let's mark that up. There's the overarching comma. Okay, so if we were to query that with a.b.c with this index expression, .d10, what's going on? We're going to take it really slowly. I'm going to break down what would happen. So overall, it's 4 things separated by a dot. That's what I do first. It's a sub-expression overall. We're using that dot notation to move deeper. But what's novel about this query? I think it's that C squashed up to a 0. Putting the name of a key right in front of an index expression. We've seen an index expression on its own and a field on its own. So what would that say in English? Well, it's going to go to the field name C, and specifically the first element of C, because C's value is an array, don't you know? So implicitly at C you'll find an array. And likewise with D, we're being implicitly told that there's an array as a value somewhere here. But this is slightly more confusing with 1 and then 0. Is this person confused? Are they unable to settle upon position 1 or the 0th position in D? And the answer is that when we place one index expression after another index expression, we are going deeper. It must be that the first position within the first array, which is a value of D, is itself an array. So we're homing in. Okay, let's show that. Okay, so placing one index expression after another, an array within an array. So if we can see that back on the actual thing that we're querying. Yep, there's the query. It's still a sub-expression, remember, overall, going from a large container to a smaller container. So in English words, this would be, okay, fine, we'll look at the code in a minute. So the query would be, let's consider only field A, and in particular home in on field B, and in particular home in on field C, whose value is an array, by the way. That's told to us by the fact that the square brackets are just there. And the 0th element of its value, of C's value. And in particular, home in on field D, whose value is an array, and the first element of its value, which is itself an array, and the 0th element of it. In a way, putting it into English like this makes it sound more complicated than it is. So execute A, we settle upon A's value, you can see that on the right. B, we move to C, squashed up to 0. C's value is an array, we can see that. The array only contains 2 elements, and we've been told from the query we're interested in element 0, which is highlighted in green there. There's the 0th, there's the first element. Okay, so that's told to us by that. So let's only focus on what we need then. Let's focus on D and its array, which is value. We have to identify the elements of this array, the one which is within the 2 blue blocks. Look for the comma. And we can now see that this is the overarching comma, and we've got the 0th element and the first element. And here we're being told we're only interested in the first element in the array, so not this one over here. There we go, and so we settle upon the 0th element. The result is just 1. Let me now raise a few puzzles with that. C's value, it's an array with 2 elements, but both of the elements are fields called D. Isn't this a problem? 2 elements have the same name. This D is ambiguous. It could be referring to this D or this D. However, let's come back. In fact, we've already scoped down to the 0th element with this here next to the C. So we know which D we're referring to. It's the first one, or the code knows. So what can we learn from this? I mean, what if we didn't scope down first? What if we just put C, not squashed up against 0 in square brackets, just C.D10. So we try this, we put it into the interactive tutorial on JMESPath.org. There's just C on its own, and we get back null. So that puts our hypothesis to bed, or ruins it. Okay, falsifies it. So perhaps that result is because it knows that there are 2 fields in C which need disambiguating, and that's why it went to null. But what if the fields within C have different names? Will I be allowed to simply put C in this situation? So we try it again. So C does not scope down. It doesn't specify which element in its value array we're interested in. And Now I've changed it from D colon and D colon to being D colon and E colon. So now there's no ambiguity. So I should be allowed, runs the new hypothesis, to just put C. Okay, so the D in our query expression is no longer ambiguous, and I get back null. So what does that tell us? It must be there's some sort of rule that says if you specify a field and the field's value is an array, a list in square brackets, you've really got to make it determinate. So we might call the error I made the indeterminate identifier. And in fact, as we go forward, we're going to see that this is one of the key things that differentiates a index identifier from something called a projection. So I'm going to point out that some queries look quite similar, and it's not sure whether it's a index identifier or a projection. And the answer is that this query, it's not, the reason it comes back with null is we've got a wrong idea of what's happening. It's not looking at the fields within C's array. All it's doing is looking at the position. In a way, it's blind to what's actually there. So it doesn't know that the fields are the same. We've got one D, another D. It doesn't know that they're different. There's just nothing. The rule is it's doing things by position. So if you're going to put C and then a later well, if you're going to put C and then something later on in your query is going to home in on a particular part of that array, because C's value is an array, you must have specified a position in the array, and that's really important. This isn't an object. We're not diving in to an associative array or a hash and picking out one of the key value pairs, are we? These are just positional items in the array. So we've now looked at identifiers, sub-expressions, index expressions, and we combined them to produce an example that took way longer than probably each of the ideas on its own, but now we can move on to slices. Not slices of bread. The better word here would maybe be range or subset. These are just fancy index expressions. They don't pick out one element, but ranges of elements. A continuous subset of an array. If you've ever used slicing in Python, then you already know how to use JMESPath slices. In its simplest form, you specify the starting index and the ending index. The ending index is the first index which you do not want included in the slice. We're going to stress that a bit more in what follows. So let's take a look at some examples. First, given an array of integers from 0 to 9, let's select the first half of the array. This is a good example. They've helpfully made the first element 0 so that it aligns with the 0-based counting. That's the input. Here's the result. What's surprising about that result? We've put 0 to 5 and we get back 0, 1, 2, 3, 4. Well, first we don't use a dash, it's not 0-5, and there's an asymmetry. We mentioned 0 in the query, it appears in the output, or the result. We mention 5 in the query, and it does not appear in the result. So it's like we treat the first value, the start value, and the end value differently. And we do. It's called the unwanted upper. The value that you name as the end value is a sample of what you don't desire. Blech. The upper bound is the first value that's undesired. It's a sample of what you don't want. So when I put 0:5, I don't want to see the fifth value in the result. You wouldn't flinch if you saw that. But that's wrong. The result will be this. 0, 1, 2, 3, 4. 5 to 10. So we're going from the fifth element, which happens to be an actual 5, up to the ninth element. we're using index identifiers still. We're not actually naming elements in the array, we're specifying positions. So this is not saying select the element named 0 to the one named 4, it's saying select the element at position 0. We could do it like this: banana, apple, orange, mango, pear, 0:3, we're going to get the 0th, the first, the second in the result. The examples can be shortened. If the start or step value is omitted, it's assumed to be the start or the end of the array. Think twice with a slice. Suppose you just saw :5. How many elements in the result? Now you're thinking, 5. I've just seen 5. But then you remember zero-based counting. 6. Oh, then the unwanted upper. Bring it back down. 5. There are 5 elements in that result. Advanced slicing. The general form of a slice is start, stop, step. Those separated by colons. Cool, right? That makes sense, doesn't it? So it's start, step, and then at the end, stop. No, the step is on the right-hand side. So far we've looked at the start, stop form. By default, the step value is 1, which means to include every element in the range specified by the start and stop. That makes sense that that's the default, doesn't it? However, we can use the step value, which is at the end, to skip over elements, for example, to select only the even elements from this array. So we could do, we'll blank out the start value, that's why it's just opening square bracket : and we've blanked out the stop value, so we've got : 2, and this is going to produce 0, 2, 4, 6, 8. Like that. So the default step is 1. Okay, we don't give a step value of 0 to achieve that, but that's not really going to trip you up because it's the default, you don't have to change it. But just don't read something like that as, : 2, repeatedly count 0 if first, second, and on every second place an element in the result. That seems sensible as a sort of idea of what's going on, because you go 0 if first, second, put that in the result, 0 first, second, put that in the result, 0 first, second, put that in the result. But of course that would mean we have 2, 5, and 8 in the result, which we don't. So you want to translate that as every element we pick stands for 2 existing elements. That's what it means when the step value is 2. So the step value is not couched in terms of count words, it's couched in terms of things existing. So imagine we were going along this array and picking things to put in the result. We always put the first element in, and this translation makes that clear. So we go 0, because we always give the first element, and you're now going to count for or represent 2 elements. So you're going to represent your successor 1 as well. It represents 2 elements, so it stands for both of them. 2, 3 doesn't need to go in, and so on. And that means we end up with 0, 2, 4, 6 in the result. Also note, in this example, we're omitting the start as well as the stop value, which means to use 0 for the start and 10 for the stop value. In this example, the expression : 2 is equivalent to 0, : 10, : 2. The last thing to know about slices is that just like indexing a single value, all the values can be negative. If the step value is negative, then the slice is created in reverse order. So we could have : -1, and that would mean that we are including everything in the result, because remember it's 1 for everything in the result, but going from the back. So the result is 987654, and I just want to point out that that means the start value is not always where we're going to start, because presumably the start value here is the default. If we look at the query, it's blanked out. They haven't put a start value, so it's the default. The default is 0, but of course the first thing in the result isn't 0, which is somewhat counterintuitive. Right, so now we've looked at identifiers, sub-expressions, and then fancy identifiers, slices. Now something slightly different. Projections. We're going to start with list projections. They say projections allow you to apply an expression to a collection of elements. Okay, collection there, it's doing a bit of work. It's saying you should be thinking of a collection, an array, no, not an array, an associative array, key value pairs separated by commas. Think back to that example involving C next to a 0 in square brackets. That is not a projection. That was dealing with an array. This is a tool for dealing with collections, associative arrays. So we're going to start with list projections, but then there are slice projections, object projections, flatten projections, and filter projections. How do I know I'm looking at a projection query? Well, we'll answer that in course. It depends on the type, but for object projections and list projections, it's an asterisk that's going to give it away. A wildcard expression creates a list projection. Remember, list, think array. So we are dealing with arrays here, but unlike the example before with C and then a 0 in square brackets, we're not relying on the position of the items in the array. We're actually perceiving particular keys in the items. So I'll try and bring that out. So a wildcard expression, asterisk expression, star expression, creates a list projection, which is a projection over a JSON array list. This is best illustrated with an example. Let's say we have a JSON document describing people, and each array element is a JSON object, something enclosed in curly brackets that has a first, last, and age key. Notice here, there is no age key, and that's an important point. They're just hodgepodges of properties. As we said, someone might not have a last name in strange examples, or someone might not even have a actually, let's not go. So people, and then star in square brackets first is going to give back James, Jacob, Jaden. Those are the values of the first keys in each element within the array. So you'll notice that the value of people is an array. In the example above, the first expression, which is just an identifier, is applied to each element in the people array. The results are collected into a JSON array and returned as a result of the expression. The expression can be more complex than a basic identifier. For example, the expression foo.bar.baz would project the bar.baz expression to each element in the foo array. Here's a few things to keep in mind when working with projections. These are discussed in more detail in the wildcard expressions section of the spec, but the main points are: projections are evaluated, extracting a value from a key, as 2 steps. So in other words, we don't actually extract any value in the first step. That's what it's saying there. They're evaluated as 2 steps. The left-hand side creates a JSON array of initial values. The left-hand side creates, that's a bit puzzling, isn't it? The right-hand side of a projection in the expression to project for each element in the JSON array. The right-hand side of a projection is the expression to project for each element in the array created by the left-hand side. Each projection type has slightly different semantics when evaluating either the left-hand side or the right-hand side. Second point, if the result of the expression projected onto an individual array element is null, then that value is omitted from the collected set of results. So don't rely on this to have a result that somehow implicitly informs you informs or tells you how many things are in there, because it's not going to include it. So don't rely on a structure that communicates things. You can stop a projection with a pipe expression. We'll get onto them later. A list projection is only valid for a JSON array. So they could be called array projections. Remember, we're on the first type here. If the value is not a list, the result of the expression will be null. So we've done people.first. We get back James, Jacob, Jaden. Now I think that if we put first dot see, I'm trying to think how this is different from the C and then something in square brackets. Well, how do these two situations differ? Well, if we look at first, its value is not an array, it's just James or just Jacob. So that example before was about an array within an array. I know James is ultimately within an array because the value of people is an array, but if we wanted, if it was people star dot first dot and then another key and then an index expression and an index expression, then we wouldn't allow first to be ambiguous the same way we didn't allow C to be ambiguous. I think that's how it works. So the left hand side creates a JSON array of initial values. And I said, how is it creating an array? Surely it's just homing in on the people field. But no, this is different from nesting. I said, perhaps it's creating because it's being selective, because it's got an asterisk in it, which means it's, even though asterisk means all of them, you could put people and then 0 in square brackets maybe, even if it's not evident here. So it's being creative because it's cutting down. So I try it out. It says, notice how people first only includes 3 elements, even the result, even though the people array on the left has 4 elements. This is because the last element, missing : different, evaluates to null when the expression first is applied, and null values aren't included in the result. If you try the expression foo everything dot bar, you'll see a result of null. Now that might surprise you. It surprised me. Why then? Because the value associated with the foo key is a JSON object, not an array. So that asterisk after the word foo essentially says this is a list projection. So we must be dealing with a value of the key which is an array. Okay, so that is saying the people field whose value is an array. This is not a sub expression. It's got a dot in it, but it's not people.first. It's not a modification of that. Okay, that would work on this, but we don't have a value that is an object like that. And remember, that's an index expression, a positional pointer. It doesn't name things, it specifies positions of things. Let's tinker with it. So that's the example we were given. We get James, Jacob, Jaden. We replace the asterisk with a 0. And we get back James. Now I can see how that works. There are elements in the people array, and we are only considering the 0th element. We replace it with a slice, 0 up to 2, the second position, with the unwanted upper, so we go the 0th in the first. So I'm going to get back James, Jacob. Go on, off you go. Good. Should there be 3 elements in the result? No. Unwanted upper, thank you. 0 up to 3, we get James, Jacob, Jaden. If we put in the asterisk there, shouldn't we get all of them? Well, as we said, there's no value for the first key in the third element of the array, because there is no first in the fourth element. It's missing : different. We're looking for values next to the key first. And that's why we describe the left-hand side as creative. It marks out the territory for the right-hand side to operate on. Left-hand side does this. This is the left-hand side in action now. So it's marked out the territory. The right-hand side gets to work now. It's looking for first. It's going within those associative arrays, key value pair, collections of key value pairs, and we get rid of one of the elements of the initial array that was created. So yeah, as I was saying, haven't we seen something like this before? In both cases, we've got a field named just before an index expression. I know there's an index expression because I can see square brackets. So why is that a projection and not that? In both cases, we have a value that's an array, so we don't have the problem that we had with foo : bar. We might say it's all about the result. The top case involves applying an expression to a collection of elements. The bottom case involves an expression matching a single element. But to me, that's kind of arguing that's circular arguing, because the point is the asterisk in the top example shouldn't work because it's ambiguous, as we said. This is a silly idea, but you might think the reason it's called a projection is because, like a projector here that produces some sort of image, we have lots of elements in the result, so that's not a projection, and that is a projection because it's got James, Jacob and Jaden in the result. Lots of elements. That's a nice idea, but slicing produces lots of elements. Just a simple slice, 5:10, and that's not a projection. So that's that. And here's another problem. We solved this problem with the ambiguous D by saying that if you specify a field and the value is an array, then you just have to specify one element of the array so that you don't have an indeterminate identifier. And that's how we excused the need for C to be next to 0 in square brackets. But that can't hold anymore because here we've got an asterisk and we're not exactly specifying one element of the array here. Anyway, let's move on. Slice projections. Okay, second type of projection. As we know, slices are just fancy index expressions. The left-hand side is the result of evaluating the slice, which may not include all the elements in the original list. So we have people : 2 dot first. So that means we've blanked out the start value. It's just the default, so we're going to go up to the first position, remember, because of the unwanted upper, and we get James, Jacob. Third kind of projection, object projections. If we look at the data we're going to work on, we've got an object as the value of ops. What's different? We don't have any square brackets inside, do we? So presumably the reason it's called an object projection is that the value of the key that we're going to name in the left-hand side, the value of the key we're going to mention in the query first, ops, is an object, is in curly brackets. I wonder if this example would still work if we had an associative array next as the value of function A. Okay, let me just read then. Whereas a list projection is defined for a JSON array, an object projection is defined for a JSON object. You can create an object projection using the asterisk syntax. This will create a list of the values of the JSON object and project the right-hand side of the projection onto the list of values. Because of course we do have an associative array here. a hash as they'd call it in some languages. We've got function A value, comma, key value, comma, key value follow, a collection. So we do ops dot asterisk dot numargs, and the result is going to be, can you guess? 2, 3. So I was just thinking about how we think about projection. They say, like, this is how you project the right hand side of the projection onto the list of values. So a list is created and we project expressions onto the list. That's how we talk. Why don't they say just query the list that gets created? And it seems that just having that bare asterisk is that's the signal to say this is not just any projection, this is an object projection. If that were in square brackets, we'd be saying this is an array projection, a list projection. So the left hand side marks out the territory. Let's look at that in action. Here's the left hand side at work. It's creating a list, and then here is the right hand side at work. And the left hand side, by the way, doesn't include the asterisk. The asterisk is a sort of middle term that unites the left hand side and the right hand side. As I said, the asterisk really is a sign just saying this is an object projection, and the right hand side is at work now, acting more like a filter. So it scans the first row, as it were. Now again, because we've got an object within an object, you might wonder whether we could just use a sub expression here. Why couldn't the query be ops dot, and then you run into trouble? You'd have to settle upon either function A or function B, wouldn't you? You could do ops dot function A dot numargs and you'd get back 2, but the whole point of this projection, object projection, is that you're going right to the deepest term straight away, numargs. You're bypassing the fact of whether it's function A or function B. This projection doesn't need to know about that. It just needs to know, 1, is it a key that is within ops? And 2, if we go right down to the other end at the deep level, does it contain the numargs key? So the right hand side is applied the same way a bouncer applies an allow list to the queue. It's reductive. In the example above, the star creates the JSON array of the values associated with the ops JSON object. So it's always creating an array, even though there's no array in the actual data here. The right hand side of the projection is then applied to the JSON array, resulting in the final array of 2, 3. Below is the sample walkthrough of how an implementation could potentially implement evaluating an object proposition. First, the object projection can be broken down into its 2 components, the left-hand side and its right-hand side. First, the left-hand side is evaluated to create the initial array to be projected. So we use this evaluate argument, which, if you don't understand, you don't really need to understand. Ops, comma, and then input data, and we've got back an array. Notice how function A, function B has dropped out of the picture. We have extracted their values, and because it's the evaluate argument function. So what does evaluate do? It extracts. It takes away the key and just looks at the value. Then the right hand side is applied to each element in the array, and it really means to each. We can't do an operation on the array, so we evaluate num args, the first object in the array, or the first element in the array, which happens to be an object, the second element in the array, and that tells us about 3. We evaluate the third object in the array, and we get back null. Yeah, the evaluate function has 2 arguments, and it's not evaluate num args and then comma 2. We need the whole object in the as the second argument. So evaluate is, in English, for the field I name before the comma, tell me what value it contains in the object I place after the comma. Okay, though the evaluate function, yeah, okay, so for the first argument, for the field I name before the comma, which is the first argument, tell me the value it contains in the object I put after the comma. So you can see that here. So before the comma we have num args, and the question is, what is next to num args? What's the value of num args in the object? What's the value of num args in variadic true? There isn't one, null. Yep, so the first stage and the second stage really are different. Any null values are not included in the final result, so the result of the entire expression is therefore 2 free. Yep, we talk about projecting arrays, meaning take the elements and apply the same operation to each. And this implies that the left-hand side doesn't project, it just prepares the ground, creating an array to be projected. Well, that's debatable, but somewhere in projection is this idea of applying to each element. So we've now looked at, as well as those basic ideas, projections, sub-expressions, index expressions, list and slice. Then we looked at object projections, like people dot first. We then, sorry, that's a list projection. Then we looked at object projections. And you can see it's the square brackets, obviously, that tell you you're looking at one kind. But we've also got 3 items in the object projection. Is it called an object projection because the result is an object? No, the result is an array, as with a list projection. So on to flatten projections. We've done list projections, slice projections, object projections. That's all of them, isn't it? Really, it's just 2. It's list projections, and which are array projections, and object projections. Slice projections, well, slices are just fancy index identifiers, index expressions, sorry. So slices just fall under array in my mind. So fall under array projections. So more than one projection can be used in a JMESPath expression. So straight away that tells us something interesting, that flattened projections are not a sort of distinct type. The issue of flattening, which we're going to see in a moment, is just removing the square brackets from which are being used to group certain values together. This issue of flattening only arises if we've got one projection and another projection, so it's not a type of projection alongside list projection, object projection. Now in the case of a list or object projection, the structure of the original document is preserved when creating projection within a projection. So I think they're saying, and that's a bit of a problem. The structure, the brackets. For example, let's take the expression reservations star instances star, in both cases in square brackets, dot state. So there's 3 parts to it. This expression is saying that the top level key, reservations, has an array as a value. For each of those array elements, project the instances.state expression. Within each list element, there is an instances key, which itself is a value, and we create a subprojection for each list element in the list. Here's an example of that. Yeah, we need to see this. So you can see the data there. We've got reservations, which is an array. The value of reservations is an array. And let's see the query. So the query is reservations instances.state. and this is the result. Now, why is the result not running, stopped, terminated, running? So the 4 words we have here, but just with one opening square bracket and one closing square bracket. I don't think I'd be massively surprised if that did come out as the result down here, just one opening, one closing. You can see again, it looks like a sub-expression because of the dots, but it's not exactly a sub-expression. We're going into reservations, that value is an array. There are 2 objects in the array. We go into instances, and then we evaluate the state key. We extract the value for this state key, this state key, this state key, and this state key. The result of this expression is this. We've got two packets, which is a list of lists. The outer list is from the projection of reservations, and the inner list is a projection of state created from instances. And they've put it like that. So R0 represents one reservation object, R1 represents another reservation object, and so the little packets here, the smaller lists, represent one reservation. What if we wanted just a list of all the states of our instances? We'd ideally like something like that. In this situation, we don't care which reservation the instance belonged to, we just want a list of states. And that's the problem that the flatten projection solves. Again, not a type of projection in itself. What we had there was a list. Were there 2 list projections there? If we look at that, they've both got square brackets, but I mean, reservations, the value there is an array. Yeah, the value of instances is an array as well. So we've got one list projection after another. Okay. To get the desired result, you can use a blanked out square brackets instead of square brackets with an asterisk to flatten a list. So we have reservations blanked out, dot instances blanked out, dot state. Try changing the asterisk to just blanked out in the expression above and see how the result changes. Well, which one? It just says try changing the square brackets with the star in, and this is an issue I'm going to explore. While the spec goes into more detail, a simple rule of thumb to use for the flatten operator is that it flattens sublists into the parent list, not recursively, just one level. So let's be clear, the parent list here is the reservations list, the key called reservations, which has as a value a list. So that's what this expression parent list refers to. So when we say it flattens sublists, we mean we have 2 lists, one that says running stopped and running terminated or whatever it was, and we are taking the contents out of them and putting them into one list. However, there could be 3 lists, each in their own little packet, and we're putting them into one. So that's what we can say we flatten the sublists into the parent list. And when they say not recursively just one level, well, this means that if reservations was in its own list, it only goes one back, so we're only going back to reservations. So that's interesting. It would be good to see an example where we had a list within a list within a list within a list. Well, the flatten operator wouldn't do that all in one sweep and get rid of all the containers, all the lists. You'd have to repeatedly apply the flatten operator. It creates a projection so that anything on the right hand side of the flatten projection is projected onto the newly created flattened list. Okay, so they do an example in the tutorial where they get rid of the second pair of square brackets. So that is the flatten operator there. And Lovely, we get something like that. So it's as if the flatten operator could speak, it would say, consider all the elements, all the positions, remember it is an index expression, and preserve their distinctness. No, that's what the asterisk would say, the one we just removed. Okay, so it's as if the asterisk was saying, consider all the elements and preserve their distinctness. Have them remember which instances array they came from. So a few grounding examples. We could put in 1 next to instances and we'd get stopped and running. Does that seem surprising? So we've got 0 and 1 and 0, 1 and 1 in that array, and you can see that we've got the first item from each instances object. So if you look at the result, it says stopped and running, and that's not from one reservation, that's cutting across. Okay, so stopped was the first item and running was the first item. I think that's a little bit surprising. But you have to remember the internal index to explain that. Here we put 1 next to reservations and we put the asterisk next to instances. Now we get these two states here, terminated and running, both appearing in the result, because this one is saying go down here. So let's take that. Reservations 1. What might someone think intuitively? You might think, if you see word N more generally, it might think it means only consider the first field, which is called reservations. Yeah, so and that's the kind of external view. So it's not saying within reservations consider the second, the first instances key down here rather than the 0th instance key. You might think it's talking about which reservations key we should focus our attention on. That's what that number here thinks. So the thought goes, and that's wrong. The index is internal. It deals with the positions of things within the reservations field. So this one here, we're already within, to the right of the reservations colon thing, okay? So the index is internal. We're talking about in here now. It's about whether we focus on the 0th item being this or the first item. Okay, and it's saying the first. And instances star is talking about, it's saying all positions internal to instances are of interest. Hence, in this example, we get terminated running because we've put instances star. Okay, watch. Consider this setup. We've got both asterisks in place. And remember, we said that if the asterisk could speak, it would say something like, consider all positions within any particular instances key, the index is internal, but preserve their distinctness. That's what the present asterisk says. Make them remember where they came from. And so we get the result on the right. They're put into their packets, running and stopped together, and terminated and running in another list. They are grouped by reservation. Okay, quick intuition check. Which asterisk is responsible for that inner grouping of the states on the right there? Is it the one next to reservations or the asterisk over here next to instances? Which one is responsible for it? Which one is causing that second, those inner 4 brackets? We've got an opening square bracket, running, stopped, closing square bracket, opening, closing. You might say, I would say the one on the left. The state values, running, stopped, etc., they're grouped by reservation. Running and stopped are together, combined, because they are within the same object. Okay, there's the object. I've just see those, there's the object. And this object is one of the elements in the outer list, the list called reservations. Therefore, the asterisk after the word reservations is responsible. Well done, that's a pretty good argument. So we run a little test, we remove the asterisk, so let's remove the left-hand one, so this query would become like that. Nice, we've blanked that out. And so we run that, oh dear. So the left-hand asterisk is not responsible for the inner grouping, the list within a list. We keep the left blanked, we remove the right-hand asterisk, and then we get the desired result. So we said well done. Well, what went wrong with this reasoning? We said the states grouped by reservation, running and stopped are together because they're within the same object. This object is in the reservations list. What exactly is wrong with that thought? Because those things seem to be true. If you look at premise 3, this object, where the object is the single reservation, the whole reservation, that is in the reservations list. That's true. That is false. Running and stopped are combined. They are combined, that's true, but not because they aren't combined in the result because of the fact that they are within the same object. So if we bring in the example again, so that's the object that is supposedly the cause of the running and stopped being put in their own little list, because it's containing both running and stopped. But that is neither here nor there, I think, because this is it's a kind of compound projection, so we're talking about flattening, but it's a list projection, the first one. So it's not, and because it's a projection, it's not even aware of what's within the object. It's just saying this is object 0. It's just all it can perceive are positions, because it's a list projection. Remember that we said the left hand side is creative. It just looks at positions. We haven't even got to the point where we're looking at what's in it yet. Does that work as an explanation? So the moral is, if you want to prevent two values called x, y from being grouped, then you must remove the asterisk from the field which is closest above them. What do I mean by that, closest above them, the field? So we have running, stop, terminated running. They're in the instances object, and both are within the reservations, so the closest field would be instances, as opposed to reservations. And you need to pull away the asterisk from that closest field to get that flattening effect. But that's a little bit bumbling and rambling, isn't it? It's hard to make that vivid. As we said back in the day, it's that closer field that causes containerization. Yeah. We can be clear with that phrase index, the internal index. That's quite helpful to remember that this asterisk here, because it's to the right of instances, it's about locating positions within the instances field. It's not saying only look at the 0th instance, for example, as we explained earlier. And because it's got the asterisk in present rather than absent, it's saying I want you to put them into little lists in the result which will communicate which of the instances field the values come from, unless you surgically remove that asterisk. We need to come back to this really. I've now realised that projection is a term from the relational model which Edgar Codd proposed for databases, so it's to do with relational algebra, so we're missing a model here, I think, but we could probably understand that why we failed the intuition check. Was it the left hand asterisk or the right hand asterisk which was responsible, by thinking about the fact that, remember, the second part in a projection is applying lots of functions repeatedly. It doesn't act on one array in one go. It takes each element of the array and applies the function. And so because the second half of that query that we looked at, that compound projection, because the second half of it was instances star, that's being repeatedly applied, and it's going to each instance in turn, and that's why that is responsible for the two smaller packets that helps me think about it. Probably haven't explained that very well at all, but yeah. So let's take this blanked out square brackets, we drop in the asterisk just like that. What's going to change? How is this result down here going to change? I'm going to press the button, here we go. That is going to cause them to be packeted like that. Running and stop together, and terminated and running. Because you should think of the second stage of the projection as we've had one, outputs an array, we then run it again, outputs an array, because we get that sequential running of functions in the right hand side. So we can call that the segregating star. Yeah, it's not running and terminated together if you look at the result. It's saying package all the positions at this instances array. And you might think that you would put running and terminated in one little packet, in one array, because the instances, the word instances in our query up here does actually sort of cut across, because remember, if we put one instead of a red star there, it cuts across. It takes the first one from here stopped, and it takes the first one from here running. So it does cut across. We get, when we put in asterisk, it doesn't cut across them. It puts running and stop together, and terminated and running together. Yeah. If you expected it to do that, well, that's just even better. So also note that it's not only empty brackets that produces flattened results. Sure, we get flat results like this. Star, we've removed the asterisk from the right. But if we put a number as our index expression, then the results are flat as well. They're not grouped on where they're from. So here I have put instance as 1, and the index is internal. So what it does is it takes the first from each instance, it cuts across, we get stopped and running in the result. And it's flat, that's the point, it's flat. And here we've put instances 0 in the query, and we get running and terminated. These values are from distinct instances fields, yet they are not contained within their own square brackets. And I thought the idea was that when we got too many square brackets, it was because it was like they were from separate instances field, and it was remembering where they're from. The conclusion we have to draw is that grouping is a unique behavior of the asterisk character. It's not grouping that's only produced by the flattened operator. Well, of course it's not. No, what I mean to say there is grouping is caused by the asterisk, so that list within a list, and it's, what I mean to say is it's not only the blanked out square brackets. Okay, so the blanked out square brackets aren't the exclusive cause of a nice flattened result, because here we've got a 0 in it. Yeah. So we've now looked at identified sub-expressions and index expressions, combinations, list projections, object projections, and ways to flatten a projection after a projection.